Greetings. In today's video, I'm working on the Fourier series expansion of this function 1 plus x squared. So the function that is taken into account is 1 plus x squared. And this function, I'm taking the Fourier series expansion of it for the default symmetrical interval minus L to L. So arbitrary L to minus L to L, where the L is arbitrary. So it won't be counted for a concrete number. Let's say if I chose minus 2 to 2 or minus 1 to 1. Instead, I'm doing just default minus L to L. And I'm creating this Fourier series expansion for this function. And how does that work? Well, basically, I will be able to re-express this function as this particular big expression, which I'm just going to show right now how a Fourier series expansion looks like. So basically, the scheme that I will be using throughout this video for the entire calculation will be, I will say 1 plus x squared, which is my function I want to express in terms of the Fourier series expansion, will be equal to a0, and this is, by the way, the default structure, the entire structure of the generic Fourier series. It's a0 plus this sum from 1 to infinity. Well, one can say n equals 1 to infinity as follows. So this infinite sum of this big argument, I'll put these square brackets just for it to be clear that it's this entire thing. It will be two things further added, so I don't have to put two sigmas instead of just one with this one big argument. And what that will be an, that's the so-called first coefficient, times cosine of, and I'm doing this on the interval minus L to L. So the formula here states that the argument of this cosine is n pi x over the L, and then to that will be added bn, so the second coefficient, times sine with the same argument again, n pi x over L. So this is the exact structure I'll be following. And of course, this is clear, the cosine n pi x over L, sine n pi x over L somehow will be integrated into the final expression. But what is not clear right now, for somebody who hasn't derived the Fourier series and doesn't know all the other parts that are needed, and the parts namely are a0, a sub n, and b sub n. These three things need formulas. And of course, these formulas, how they have been derived and how this entire Fourier series has been derived, there's so much to be said about it, but right now I'm working with a concrete example. I'm trying to re-express 1 plus x squared as a Fourier series expansion. So I'm not going into all those things, but I am using the formulas for these three things, namely a0, which is the first term, which, by the way, can be rewritten, this entire thing can be written in the way that a0 disappears and it becomes part of this, that this starts at 0, there's certain changes, but for a certain reason, because of a certain realization, a0 is kind of separated out right here, and it simplifies everything in the end, and then this starts as 1, goes to infinity, and we further have an and bn. So, a0, the formula for a0 is as follows. It's 1 over 2L times the integral of from minus L to L of the function that I'm re-expressing. So it's 1 plus x squared in this case. I'll just write it that way, in this case, dx. So what I'm doing here is that I'm basically giving an expression that will replace the a0. So this is the structure that has to be followed. This is the structure that's getting followed, but a0 is also equal to 1 over 2L times integral from minus L to L of this argument of the very function that I'm actually taking the Fourier expansion of, just dx. So taking this integral will cover the a sub 0 for me. Also, what's often seen is a0 over 2 as being first part of this Fourier series scheme. So one might see, instead of just a0 here, one might see a0 over 2. And the reason for it is basically here it is 1 over 2L. For these other coefficients, it will be just 1 over L in front of the integral, or whatever integral that will appear in a second when I show the formula for those two as well. But here I have 1 over 2L. So basically, when one says a0 over 2, that means that one sees the a0 as just 1 over L. So one compensates for this kind of small neglect by making sure that the a0 is divided by 2. But if a0 is already defined as 1 over 2L multiplying this integral, then a0 by itself is what is used. Alright, so a0 over 2 is used when this 1 over 2L is not there, but there is just 1 over L in front of the integral. But as long as there is 1 over 2L realized right here, then there is just a0 without the over 2. So there's like mutual compensation in case one part does not have it like 1 over L is only, then of course A0 over 2 will be used. But if it has 1 over 2L inside the expression for A0, then I just use A0 right here. So that's it. So that's the first part. It will be the shortest expression. Actually, I might leave it there, just it doesn't take up too much space. I can leave it there for now. So it's 1 over 2L times integral from minus L to L of the function 1 plus x squared dx. And by the way, it will be probably the easiest part to get. So basically where all the time will be spent is on realizing actually some things will get cancelled out throughout the way. Therefore, that might be the first time-consuming thing inside of during this process of finding the Fourier series re-expression or expansion of this 1 plus x squared function. And another very time-consuming thing is basically calculating these coefficients, for which I'm just giving the expressions now as well. So A0 is as follows. Then we have an. And what is an expressed as? Well, an is 1 over L times minus L to L, so the same integral bounds. But the argument will be a little more complicated. So again, 1 over 2L was here, but an is just 1 over L. And there's no need to do an over 2. No. It's just 1 over L times integral from minus L to L. That's it. Then it is the function, so in this case 1 plus x squared, multiplied by the same thing, like will be next to the coefficient anyway. So it will be multiplied inside this integral as well by cosine n pi x over L. Alright? So this entire integral gets solved, then becomes the coefficient an, and then again, anyway, it is still multiplied by this outside cosine n pi x over L. Alright? So this is the expression for A sub n, and for B sub n, it is 1 over L, so the same 1 over L in from the integral, again, integral from minus L to L. Again, the function that is chosen, which in this case is 1 plus x squared, and it gets multiplied by the sine n pi x over L. So that's quite easy to remember that indeed for the Bn, it is sine that multiplies the function inside the integral argument, and in the case of the an, it is the cosine n pi x over L that multiplies the function that we are taking the expansion of inside of this integral's argument. Alright, so these are the three expressions for these three coefficients or these three things. This is a term by itself, but these an and bn are actual coefficients, so these two coefficients and this a0 term. With these expressions, I can just solve slowly and I can get this entire Fourier expansion. But there's a thing that is worth realizing before starting or before diving into it completely, and that is the question of whether if the function I'm re-expressing is odd or even. And the reason for this is actually that in case it is, for example, odd or even, it might influence the fact that actually some coefficients might cancel out. And the reason I wrote here the expressions for those coefficients is as follows. I can figure out whether if something of this entire expression will cancel out and basically save a lot of time and simplify the entire process on the basis of realizing whether if the function I'm expressing in the Fourier series is even or odd. So in this case, it is an even function. It's an even function. What does that mean? Well, basically it looks something like this, right? So f of x will equal to f of minus x. That means if I input minus 1, it should give me the same value as if I input 1. If I input minus 100, it should give me the same value as if I input plus 100. It means it's symmetrical about the y-axis as follows, right? If it was odd, it would be symmetrical about the origin. It means it would look like this, kind of. Something like x to the third power, for example. And that would be an odd function. Now, what's very important with this is not only realizing that 1 plus x squared is an even function, but also applying it in practice right here. Because bn and an, if either of them are 0, then these entire parts of the Fourier expansion will disappear. Because if an is 0, then this entire part becomes 0, just disappears. If bn is 0, then this entire part disappears. And there is actually a good realization for integrals in this context. So when one has a an even function, then the integral will be basically, if it's from minus L, especially now that it's symmetrical, as I'm doing here, right? Minus L to L, it's to the same distance to the left of the y-axis as it is to the right. So if it's minus L to L, it will basically be the same like the integral from 0 to L counted twice. And in case that my function is odd, as follows, then it will mean that the integral on the interval from minus L to L will be equal to 0, because what gets added on this part will get subtracted on the left of the y-axis, the same amount. So this is worth taking into account. And the cases when the actual arguments of the integral, so it's not only about the function, but it's also in combination with sine or cosine, or however the two things are combined inside the arguments that are part of the expressions for bn and an. Based on that, I can decide whether if the integral will be 0 before even calculating it, because actually very often it will take like integration by parts to finish off this, and that takes a lot of time. So instead of doing it, first I will check whether if the argument does not actually tell me that the entire integral will become 0, although I didn't even calculate it, I can tell in advance using this idea. So basically, if I look, for example, at an first, so I have 1 plus x squared here, and it's multiplied by cosine n pi x over L. It does not really matter, it's n pi x over L. Basically, cosine, one can say, it is even function. It's an even function, no matter what L is, but it has something like this shape, right? So it's like a shifted sign. But the fact is, it's because it has this value 1 and it falls the same way to both sides, to the left side and the right side of the y-axis. It is symmetrical above the y-axis and it is an even function. Cosine is an even function. And if I multiply an even function, and this is, by the way, the same kind of idea as like multiplying minus times minus is plus. Multiplying plus plus times plus is plus. And I might do a separate video on this, because this is a very important and interesting and not that complicated topic when clearly, slowly, and basically with diligence, delivered. It can be a topic quite very useful to understand. Therefore, I might do a separate video for it. But anyway, if I have a function that is even, which is my function I'm re-expressing right here, and a function that is not even, or that is even, let's say I'm still talking about an. So if I have a function that is even, and another function that is even as well, multiplying it, the result will be an even function. That's the rule. Alright, so the rule says that if I have one even function and it's multiplied by another even function, it will be still an even function as a product. The product of these two functions will still be an even function. That means that although I might simplify this thing in the way that I'll just do 0 to L and then put 2 in here, then I'll basically just take half of it to the 1L and then multiply it twice because it's same to the left side and to the right side. It's not odd in the way that it would subtract itself from itself, in the way that this would reduce to 0. So in the case of a sub n, I see because the result that this product gives, the product of my 1 plus x squared, which is even, and cosine, which is even, is still even of a function. That's my rule. When two even functions are multiplied by each other, they give together a new even function. Because of that, this term does not reduce to 0, because although it's on this symmetrical interval, basically it will be this entire area. It will be whatever it will be on both sides of the y-axis, but it will be on both sides positive to give, or it won't subtract itself from itself. So it won't subtract that one side from the y-axis will subtract the other side from the y-axis of the function. But with Bn, I might look at this again. And I might check if in this case, this argument is an odd function. In such case, it would reduce to 0 and Bn would not be counted in this Fourier expansion at all. So I can figure out this thing. Well, 1 plus x squared again appears here. It's still even, but it's multiplied by sine. And sine is an odd function. I won't draw it here anymore, not to cause more confusion, there's already enough curves. But just realize psi is an odd function, and the rule says just like even times even is still even times odd is actually odd. So it's like plus times minus is minus, odd is the minus kind of idea. So when I had this even function and I multiply it by this odd function, the result is that together they are an odd function argument. Alright? And an odd function on a symmetrical interval, basically it's like minus L to L, like this. Well, what gets subtracted here, right, this area, it will get added here. It will get added here. Alright? Therefore, the Bn reduces to 0. It's an even function times an odd function. Together it's odd, and therefore the Bn reduces to 0 in this particular case. In other cases, if, for example, this was an odd function, there was some other function and it was odd, then it would not reduce to 0. Alright? So for that reason, I will not have to do Bn. And the only thing that is left for this concrete Fourier expansion is the An. Alright, so I can just go straight into it, and I can start with A0. So after this lengthy kind of introduction or reasoning for why the Bn is not counted or why it's cancelled out of the process, I can finally start with applying these expressions for A0 and also An. Bn actually won't be needed at all. Alright. So calculating this is like calculating a normal integral. What I will do is basically take the integral in respect to x plus x to the third over 3, and 1 over 2l in front, right? So it's 1 over 2l right here. And this entire thing gets evaluated at L and minus L. Alright. So just to check, it's x plus x to the third over 3. Evaluated at L and minus L. And all that multiplied by 1 over 2l. So what is that? Well, it's 1 over 2l times, and now I will first plug in the L, which is L plus L to the third over 3. And then I will subtract, and I will plug in minus L. So it's minus L minus L to the third over 3. Alright. So what does this altogether give? It's 1 over 2L times L plus L to the third over 3. And still, this is far easier than the next integral will be, because I will be doing the A sub n using integration by parts. And it will be a little more lengthy, so it's plus L plus, actually this ends up being plus again. So plus L to the 3 over 3. And so the result for this, I'll just write it right here. It will be 1 over 12. I might modify it later, times 2L as these parts plus 2/3 L to the third, I guess. So it's 2/3, 2 times L to the third over 3. Alright, 2/3 L to the third. Alright, so that is for the A0. So that is taken out of the way now. And now I can solve for A sub n. And A sub n will be slightly different. A sub n will be slightly different. And it will be slightly more complicated. It will take a little more, or a lot more, in other words, a lot more time. Alright, so how is this calculated? Well, it is the 1 over L, integral of minus L to L, over the function 1 plus x squared, multiplied by cosine of n pi x over L. And it's already visible, I have to do double integration by parts. And there's basically a simplifying rule to do this. But in this case, I just want to do the traditional way, just integration by parts without utilizing some shortcuts. I might do a special actual video on that in another one. So in this case, I will do the integration by parts. It will take a little moment, but hopefully without mistakes. And in the end, although there will be big parts that will be integrated many times after each, again and again, because of the integration by parts, a lot of it will cancel out, and I will show why in a second, or when we get there. So, for now, integration by parts, I will just have to be writing this 1 over L a lot. So basically what I will do, just say 1 over L, then this entire big thing, then I will be evaluating at L and minus L. And inside I will do the scheme for integration by parts. So let's say this is u, and this is the derivative of v. Cosine and pi x over L is derivative of v, and 1 plus x squared is u. Therefore, the integration by parts scheme is uv times integral of u prime v dx. Alright? So basically u gets rewritten first, that's 1 plus x squared, stays like that. V will be the integral of this, which is slowly sine of n pi x over L times the inverted rest except for x, which is L over n pi. Alright, and then minus this integral, which will be u prime finally decreased by 1 degree, so 2x now. And then multiplied by basically the same integral, so it is sine of n pi x over L, all of that multiplied by L over n pi. So actually I will move this further out, multiplied by L over n pi as follows. Alright, dx. And this entire thing should be evaluated at L and minus L, but again this L minus L will get rewritten again because I have to do more calculation to this. So it's 1 over L, then I can write this part, which by the way, it's not very important if I do this right because this thing will disappear. I will explain in a second. It's thanks to the n pi multiple right here, it will be actually 0. But anyway, not to confuse you, I will just write it for those that, for most people, because it's still not clear why, because I didn't mention it explicitly why this part will disappear. Then L over n pi right here, alright? And then from that I subtract this integral, which this integral I will further re-express, I put it into parentheses like this. And now I will delete the previous integration by parts scheme and I will create a new one. Again, this will be u and this will be taken as v prime. So I will leave this here. Okay, so I could have moved it out, but I will leave it there for now. So u, then what I do is basically the minus and then is how I rewrite this integral by itself. Well, that will be basically u I rewrite the same, so it's 2x. Then I multiply by integral of this, which is minus cosine. This will become a little not very nice anymore. So in the same height, minus cosine of n pi x over L, still the same argument, times minus cosine, and okay, so I'm taking this entire thing as v prime. Alright, so just to be careful about that, it's times L over n pi, all of that entirely squared. Alright, and then from that I will subtract basically the integral, which will be u prime times v dx. Alright, and once I have done that, this will end, and all of it still gets evaluated. Just rewrite this part, and L and minus L. Alright, so hopefully still no mistake. This finally gets just reduced to a constant, just 2, which is nice. That's been the goal all along. And sine, well, again, like here, just to be careful, minus cosine in the same height again, minus cosine of n pi x over L. Alright, but there's L over n pi, and so this is L over n pi squared now. Alright, and we're finally getting almost to the complete end. So it's 1 over L, then I'm writing this part just because it's not the end yet, I'm just keeping this for the sum up to the end. As follows, L over n pi. Then minus this one, I'll just put it there, and it's minus, so it's plus 2x times cosine, I'll put the L over n pi squared in front as follows, then times cosine n pi x over L. Alright. So that is cleared up. Nicely. And then this is minus, so it's a plus. This integral. And what I can do is actually I can take out the 2 times L over n pi squared out of the integral first, and then I can just keep the cosine. And by the way, was it this was minus, but this is minus, so it's plus. Yeah, as I said before. Minus 2 times L to the over n pi, all that squared, then times the integral of the cosine of n pi x, so there will be L over n pi to the third soon, pi x over L dx, and all of that gets evaluated ln minus L, and finally, hopefully, everything will end up correct. It's 1 over L times all of this, so just rewriting sine n pi x over L times L over n pi plus 2x L over n pi to the second. This is the most important part. And by the way, I did have to really be careful about this part because it will change to sine, and again, in a second, it will be explained why that is. Basically making it a redundant part of the solution. But I'm just writing it anyway, just not to confuse anybody. Alright. So it's like that, hopefully. And all of that, L and minus L. Alright, so after this very long kind of integration by parts, and again, there might have been shortcuts, there are shortcuts to this repeated integration by part. I didn't use them just to do the classical integration by part if somebody wants to. And now finally we got almost to the end, almost to the result for A sum n. So what I can do is just use this end result and delete these preceding calculations, which the upper bound still the same. And what I will do is basically draw an arrow just to indicate the result for an. So I'm integrating all of this, but I'm evaluating at L and minus L this entire thing. So I'm doing 1 over L, and then I'm slowly going to be evaluating. So again, here 1 plus x squared, or not again, just finally evaluating 1 plus x squared times L over n pi. Well, I can plug in L and minus L there, right? Possible. And by the way, before doing this, I could have of course considered doing L and 0 and then putting 2 here, but it doesn't really matter. I can do either. Well, it won't really reuse that much of the time that has been needed or that will be needed, so it's not very important in this particular case. It won't save that much time, so I'm not doing it. I'm not changing this to 0 to L and then multiplying it twice because it's symmetrical and odd of a function integrated over that over the symmetrical interval. So finally, now I can start plugging in the L. And if I plug in L here, well, L will be x, so L over L will cancel out, and it will be sine of n pi. And no matter that there is 1 plus x squared and L over n pi, this cancels out, even with the minus L. Oh, again, it's minus n pi. N pi, sine of n pi is 0, sine of minus n pi, when n is of course considered as some integer, then of course that's 0. So this term, because there's this sign, that will end up being sine of n pi because of the L inputted and minus L inputted, cancelling out with this denominator in the argument. This entire thing becomes 0. Alright, so that is 0. Then the same thing becomes for this other part that I said I don't have to concentrate on much because it becomes redundant anyway. Again, if I put L here, it just becomes n pi, it is 0, cancelling out the rest of it as well. Minus L again, minus n pi, 0 as well. So I can cancel out all of this. And the only thing that is left is 1 over L of actually this part. 2x times L over, and by the way, this can be taken out, L over n pi squared. So L over n pi all that squared. And I'm doing 2x cosine n pi x over L minus L. Alright? And now finally we're getting very close to the solution here, just to check 2x cosine n pi squared. Alright, very nice. So now what I'm doing is basically I'm plugging in the ln minus L. So it's I can take care of this a little bit. So this will basically end up L squared over L, so it's L over n pi all that squared. And when I'm plugging this, well, it gives first, the first parentheses will be positive L, so 2L times cosine of basically what this will give n pi, because L will be here, right? And what is cosine of n pi? Cosine of n pi, actually I did it in the previous Fourier series video from the past. It's equal to -1 to the n. That means if it's 1, for example, cosine of 1 pi, it's -1. Cosine of 2 pi is 2n, so n is 2, so it's 1 again. It will be the value, right? So that's the reason cosine of n pi is -1. Because the L cancels out with the denominator L right here, it becomes cosine n pi when evaluated. So it's 2L, that's for the x, and then -1 to the n. Very nice. So the only thing that survives as a non-number thing is the n right here. And the next part is the second parenthesis, I subtract the lower bound, which is minus L, so it's 2 times minus L, so minus 2L. So again, this will nicely add to it. And cosine of, when I plug in minus L here, it will be minus n pi. Well, minus n pi, what it is basically, I can draw it. So minus n pi should again be -1 to the n. If one gets -1, cosine of minus pi basically, because this will be n pi minus n pi, so when one gets cosine of minus pi, it will be -1. So again, it is -1 to the n. If one gets cosine of -2 pi, it will be n equals 2, and it will be -1 to the 2, so the value will be 1. So again, cosine of minus n pi will be -1 to the n again, as follows. And now I can rewrite this yet again. Well, what this gives is L over n pi, n squared pi squared, I can say. And then inside this, it's basically 4L is 2L times this plus 2L times this, so it's 4L times the same -1 to the n. Alright, so what do I get? Well, in the end I get 4L squared -1 to the n over n squared pi squared. Beautiful. So this is the result that I got as the coefficient for the AM. And now all I have to do is take this initial structure and plug it in. Because the Bn cancel out, the only An and A0 are there, and I will plug them both inside into the final result. So hoping that everything was correctly calculated, I can finally come to the final result, which is 1 plus x squared equals A0, which was calculated to be, and I said I was gonna change this, just simplify it, so 12 over 12 is 1 plus 2L to the third over 3 times 1 over 2L. Well, what is that? Is this 2 first L to the third? So this is 2, just to make it clear. So it is 1 plus L to the second over 3, I think. Over 2, that's cancelled out. And then L to the second over 3. Alright, so basically my Fourier series expansion should be as follows. So it's A0, that is this, I just calculated 1 plus L to the third over 3 plus this sum from 1 to infinity of n right here. And what is that? Well, that is this coefficient An. So it's the coefficient 4L to the second times -1 to the n alright, over n squared pi squared multiplied by cosine of n pi x over L. Alright, that's the entire argument of the sum. So this is finally the Fourier expansion from minus L to L of the function 1 plus x squared.